Hi everyone. In this lecture, we're just going to briefly cover thiols and sulfides. So we're not covering these in too much detail, but thiols are the sulfur analogs of alcohols. So let's write that down. So thiols are essentially alcohols, but instead of an oxygen atom, we have a sulfur atom. Now, one thing about sulfur compounds is that they do tend to smell really bad. So oftentimes we try to avoid using sulfur compounds, but sometimes they're pretty useful. Now, remember, sulfur is larger than oxygen. It's further down the column on the periodic table. So that will affect your molecules. Now, let's look at a couple of compounds. So we'll look at an alcohol and a thiol and see how we name them because they're pretty similar. So for instance, let's say we have the following alcohol and then the following thiol. So let's count how many carbons we have in the longest carbon chain. So let's see, for the alcohol, we have 1, 2, 3, 4 carbons in the longest chain. And it's the same for the thiol. So the way we would name the alcohol, let's see, we would use butanol to start. So that tells us we have 4 carbons in a chain, and then we have an alcohol somewhere on that chain, and it's at position 1. And then we have a methyl group at position 3. So that would be 3-methyl 1-butanol. And remember, we use OL to indicate an alcohol. Okay, so what if we have the SH group instead? Well, it's pretty similar. We're going to name this 3-methyl 1-butane thiol. So we keep the E on butane, but we just add thiol to the end. So not too different from naming alcohols. Now, what if we have a compound with a thiol and an alcohol? So what if we have this molecule? How would we name that? Well, again, we're going to count how many carbons we have in our parent chain. So again, we have 4. And the alcohol actually has priority over the sulfur group. So the sulfur group is considered a substituent, and we would call that a mercapto group. Kind of an interesting name. So when we're naming this, we would say 3-mercapto-1-butanol. Okay, and let's just briefly cover how to prepare a thiol. All right, so we're going to start with an alkyl halide, and then we're going to perform a substitution reaction. Specifically, in this case, an SN2 reaction because we have a primary carbon. bonded to our leaving group. And we can use something like sodium bonded to our thiol group. So the thiol is negatively charged, and that's going to come in, or I guess it's a mercapto group, but that will come in and our leaving group will leave, and we'll end up with the thiol molecule. Now remember, if you're performing this on, for instance, a secondary carbon where you could have a stereocenter, remember that SN2 involves inversion of the stereocenter. Okay. All right, so now let's look at disulfides. So disulfides are really important, especially in biology. Many of our proteins or peptides have disulfide bonds that are holding or creating the shape of a protein or even a peptide. So if you're taking biology right now, I'm sure a lot of these words sound familiar. If you're not taking biology, that's okay. We'll just kind of go over the chemistry here. All right, so let's say we have two thiol molecules next to each other. We can actually combine those together to create what's called a disulfide, where you have two sulfurs bonded together. So the way we would do this is through oxidation. And for this particular reaction, we would use bromine in, let's see, an aqueous sodium hydroxide solution. So sodium hydroxide mixed with water. Now, what if you wanted to go in the other direction? What if you wanted to break the disulfide bond? Well, you could use a reducing agent like zinc with hydrochloric acid. So again, disulfides are important in biology. So for example, if you've heard of the amino acid cysteine, oops, my C looks like an E. Let me rewrite that. So cysteine amino acids contain a thiol group. And if you have, let's say, an amino acid chain, and you've got some thiol groups kind of coming off, those can combine together to create a disulfide bond, and this will hold the chain of amino acids in a particular shape. All right, and certain proteins need to have specific shapes in order to perform their functions. So for instance, enzymes need to have a particular shape so that they can hold on to molecules and help them react or break apart. So these disulfide bonds can help with that. All right, and then the last thing we're going to talk about are sulfides. So sulfides, you can either have, for instance, the sulfide ion bonded to a metal atom. So maybe you have magnesium sulfide or, something like that. Or you could have a sulfur bonded to two alkyl groups. Now, what's interesting here is that you can oxidize a sulfide and turn it into the following, where you have an oxygen double bonded to sulfur. And I believe there's still a lone pair on sulfur there. So in this reaction, we took a sulfide and we turned it into sulfoxide. And we used something called sodium periodate. I believe that's pronounced periodate. I always have trouble pronouncing things for some reason in chemistry. I'm sure some of you can relate. There's some weird names in chemistry. Okay, and this is actually a gentle oxidizer. So this will allow us to stop at the sulfoxide. But if we had a stronger oxidizer, we could actually go one step further and form something called sulfone. Or sulfone? I don't know. All right, so remember that sulfur has an expanded octet, which is why it can bond to so many different groups. And for instance, in the last molecule we drew, sulfur has 2, 4, 6, 8, 10, 12 electrons. And that definitely violates our typical octet rule. But again, sulfur has an expanded octet, or it can have an expanded octet. And probably the best example of this is SF6. So you might recall this from previous courses. So here sulfur can bond to 6 different fluorines, and it has 12 electrons that it's sharing. All right, so back to our reaction down below. To go from sulfoxide to sulfone, we would use hydrogen peroxide, and that is a strong oxidizer. So if you wanted to skip the middle step and just go straight from the sulfide to the sulfone, you can use hydrogen peroxide. All right, and that's really all I had on thiols and sulfides. Again, they can be really useful, and we saw the example of disulfides, which hold amino acid chains in a particular position. But really, this chapter focused more so on ethers and epoxides. All right, so in the next chapter, we're going to start discussing mass spectrometry, and we're also going to review IR spectroscopy, and we're going to kind of combine the two to help identify different compounds. So I will see you in the next set of videos.